Okay, good morning, everyone. I don't know, you might have maybe some problematic with that projector. So if you could, we probably need to wait for a while for that one to show up. So if you could, you can sit on here to look at this one. Right. Okay, so thanks for coming. This is the final lecture of our class. So we're gonna first give a quick guidance for the final review, and also, reinforce some the schedule and also some policy for the final exam. Then we'll give some like practical advice for machine learning practice. Okay, first, our final exam, as we emphasized in Canvas announcements, it will be on December 9th, which means like next Monday from 8 a.m. to 10 a.m. It's pretty early time period, but it's not decided by us. It's decided by university. Right? The good thing is that we're gonna do the Canvas exam, which means that you can do that at whatever place you feel comfortable. And on next Monday, like say at 8 a.m., please open the Canvas and look at the quizzes section. You see one final exam available, and you can click into that and do the exams. And again, we're gonna keep posting the schedule of final exam on Canvas, right? To keep reminding everyone and make sure like no one's gonna miss it. Okay, so policy. We mentioned that before, but here we just want to repeat, right? So it's open book, open website, meaning that you can prepare any slides or anything you feel like comfortable, feel helpful with your exam. And also you can open whatever website, you can even search on Google. That's fine, right? But do not search and post questions online, right? Do not post the questions like on any QA website like Stack Overflow. Most of the problems, as we mentioned, are single or multiple choices. And also there will be a few text description problems, like mainly asking you to write down your understanding of something, right? Or analyze something, but there's no need to write any math formula. There's no LaTeX. But here we just want to emphasize like this is like a big library of the problems. So everyone will be like when the set of problems you have might be different from the set of problems your fellows have, because it's kind of like randomly chosen. Of course, there will be some like large overlap, but it's not exactly the same. Okay, any question regarding the schedule and exam policy? Okay, great. Then we'll just keep bugging everyone through the Canvas announcement. So don't don't get annoyed. This is just to make sure. We just want to keep broadcasting to make sure no one's gonna miss this, right? Okay. So what's the range of the final exam? The coverage will be the whole semester. So that's why it's called final exam. Now here's our suggestion, like for effectively reviewing. We don't want to occupy too much of time of doing this. So we will ask you guys to review the lecture slides and also go through the paper problems in the homework assignments. So don't worry, there won't be any programming questions. But those paper problems might be helpful because in paper problems, I mean, you can just get rid of those calculation questions, like ask you to calculate what is information gain, was Gini index gain. We're not going to ask you to give some calculation for that. We just want you to understand what's the meaning for that, right? And doing this can measure, the label purity after splitting data. Right? You should know that, right? So that's why we believe like going through paper problem might be helpful because it's kind of like strengthen your understanding on the motivation of the algorithms we have gone through. Okay, so so here we just want to quickly go go through what we have discussed throughout the semester as kind of a lead for you to do a review, right? So throughout our semester, we started discussing the definition of machine learning, right? And then we brought out like the framework of doing machine learning. Mainly we focused on supervised learning. Then under this big framework, we introduced a variety of learning models and algorithms, right? And also introduced different learning principles, right? Like empirical risk minimization, regularized risk minimization, Bayesian learning, and so on, right? And also introduce some preliminary concepts in computational learning theory, right? Like what is the generalization error, also known as true error? What is the training error? What's their relationship, right? So remember when we talk about the computational learning theory, we'll talk about the very ideal case, which is called consistent learning. You always have a zero training error. Then to get a particular level of the generalization error, at least how many training examples would you want, right? This is sample complexity. Then we switch to a more realistic scenario, which we call agnostic learning. What is agnostic learning? Anyone recall? Yes, exactly, right? This is actually the practical assumption, right? Because you're not, in many cases, you actually do not know what is the true labeling function is like, right? We call it like concept. You actually don't know which particular family of functions your true concept belongs to, right? You have to assume, okay, it belongs to this one, right? Or you kind of craft a large, rich family of functions. You believe searching over these functions can find a good approximation, right? So that's the idea. But that means like in agnostic learning, you won't guarantee your true concept will be inside your hypothesis space, which implies your training error will no longer be zero, right? It could be bigger than zero. And then we use some probabilistic bound, which called tail bounds to quantify what's the relationship between the generalization error and the training error, right? So if you could recall, right, we know the generalization error is upper bounded by the training error plus some term, right? That term kind of like determined by the complexity about the hypothesis space you search over, right? So that actually justifies the Occam's razor principle, right? And meaning that okay, if you use like several hypothesis spaces, each of this hypothesis space can give you like the same training error, then you're gonna choose the simpler hypothesis space. Why? Because it can tighten the generalization error bound, right? Right. So yeah, so please connect all those concepts together, right? We'll just want you to understand those basic concepts and their relationship. We don't want you to prove anything. We don't want you to prove any inequalities or theorem. It's not like that, right? Then we'll talk about implementation of those algorithms and in practice how we gonna use them, right? So that's mainly examining our homework assignments, especially the programming assignments, right? That won't be tested on final exam. Okay, so first, what's the definition of learning, right? Although we talk about several definitions of learning, but the most modern and formal definition comes from Tom Michel in 1999. So we say a computer program can learn from experience E with respect to some class of tasks T with some performance measure P if its performance at tasks in T measured by P improves with E, right? So basically it tells that, okay, if you want to say, if you want to claim your computer program is a learning algorithm, means that giving you some training data, you should do well. You should do better than without such training data, right? But do well means that it's not like you're just doing well in training set. It should be like you're doing well in the overall task. That's why we say learning essentially is to gain the ability to generalize. Okay. So then we talk about what's the framework of conduct machine learning, right? So basically, we need to define what is the instance space, what is label space, right? So the learning essentially is trying to find a mapping, trying to function which map an instance in the instance space to a label in the label space, right? And the label space actually determines what the type of the learning problem is, right? If your label space is binary, like positive or negative, then you're doing binary classification, right? If you have like multiple discrete values, it corresponds to multi-class classification, right? If a label is continuous, this is called regression, right? And the underlying assumption is that we have some like a concept, we have some true concept, which we also call target function, which gives the ground truth label, right? And the goal of learning is to find or approximate this target function. Okay? So to achieve that goal, you're gonna prepare a set of labeled training examples, right? So basically, it's a pairs of instance and their ground truth labels, right? You want to use this set of training data as a guidance to help you search over some hypothesis space, right? So these are done by this, black box learning algorithm. So after learning algorithm is done, right, it should return a learn function G from your hypothesis space. This G also maps X to Y, right? So this is called supervised learning. And of course, we mentioned that you can, by altering the training data, you can come to other learning protocols. Like for example, if I remove all the labels, this is called unsupervised learning, right? If you use partial label data, partial unlabeled data, it's called semi-supervised learning, right? But it's not scope of our class, right? Okay. So we mainly talk about supervised learning models, right? So we talked a lot throughout the semester, right? We start with the decision trees. Like why decision trees is not like the simplest machine learning model, but it probably they are the most intuitive one because it's very similar to what human beings are doing classification and decision, right? That's why it's a decision tree. I want to find out some like discriminative nature feature, and then according to the feature choice, I'm gonna reduce my decision of thinking into a subset of by looking at a subset of variables and so on, right? So it's kind of like a divide and conquer and recursive decision process, right? And then we'll talk about boosting and ensemble. Boosting ensembles are a type of methods which can assemble a set of weak classifiers to make them super strong. Right? And most boosting and ensemble learning approaches are based on very shallow decision trees, more specifically decision stumps. So decision stumps are what are decision stumps? Yeah, very shallow decision trees, right? In particular, you have only one level, right? That means you only choose one feature to split on the data set, right? And the ensemble learning actually consists of like two big types, right? One is called ADA boosting or boosting, right? Boosting means that, okay, I'm gonna sequentially train a set of weak classifiers, right? And the next classifier is trained based on mistakes made by the previous classifier, right? How can we do that? We're gonna accord to the mistakes made by previous classifier. We're gonna reweight every training example, right? And we amplify the weight for those mistakenly classified examples in the previous run and demote those examples that have already been correctly classified, right? So as the iterations proceeds, right, we want, oh, here we go. Oh, it took a really long time. But as the iteration proceeds, the classifier, the weight classifiers will focus more and more on those wrongly classified examples, on these more challenging examples, right? And then we just assemble them together to make the final prediction. The ADA boost uses a linear combination for the assemble. Right? And another type of approach is called ensemble. It's called like random forest trees, right? Or bagging. So that's even more straightforward. It doesn't assume you must have some like weight classifiers. You just train a model to be as overfitting as possible, right? But every time you're gonna resample the data. Resample the data means that, okay, I treat the original data set as a data source. I just run them, resample them and retrain the model. They also mainly use decision trees, but they let the decision tree to grow as large, as deep as possible. Why is that? There's some like formal analysis we have discussed previously, right? So remember, throughout the decomposition of the generalization error, we found the generalization error can be decomposed into the summation of the bias term and the variance term, right? So the more complex, the more expressive your model are, the smaller the bias, right? But the larger the variance. Why? Because your model is very, if you have like a super big model, right, the model will be very sensitive to the variation of the data, right? So that means like the prediction itself will have a large variance with respect to the training data, right? So it turns out that, okay, your generalization error is not only up to the bias, but also decided by the variance, which reflects the nature of your model. So you can intentionally train a super big, super deep decision trees to have a very small bias, but meanwhile, but you kind of like increase the variance. Right? How can we reduce the variance? We just repeatedly resample the data and retrain the decision trees. So then when you take an average, we know that taking an average is a very effective way to reduce the variance. So you can imagine like now I have a very small bias. I have taken an average of all my deep decision trees. I have significantly reduced the variance. So put them together, I can substantially reduce the generalization error. So that's the key idea of those bagging method and random forest method. Okay. And then we start talking about the linear models. Right? We start with least mean square for linear regression. And this one is pretty straightforward. I believe most of you have seen them before, but we talk about what is stochastic gradient descent, right? And what's the idea of a stochastic gradient descent? Then we start talking about linear classifiers, perceptron. Right? Perceptron was is a mistaken-driven algorithm, online algorithm. I just keep processing my training examples one by one, right? If my current model correctly classifies this example, I do nothing, right? Otherwise, I'm going to update my model parameters according to some rule, right? Which is called perceptron rule, right? And we talk about some theoretical guarantees about perceptron, right? You should know what's the behavior of perceptron. If the data is truly linearly separable, will perceptron converge? Yes, right? We have shown that, right? We actually give the upper bound of how many iterations at most the perceptron need to converge, right? However, if the data is not linearly separable, the perceptron will enter into an infinite loop, right? It will just cycling through a set of distant weeks and forever and ever. That's why in practice, you will never like let the perceptron go forever. You will just set a maximum number of iterations, right? And remember, in practice, I mean, to let perceptron work more robustly, well, we have several variants, right? We have voltage perceptron, we have average perceptron. Okay, and then we proceed to the support vector machines. This is like one of the most important topics in our class, because support vector machines, before the resurgence of neural networks, is dominates the whole area for 20 years. Right? Even right now, it's still like one of most widely used approaches, especially when we have like very few data sets. SVM works really well, right? Support vector machines are motivated from the computational learning theory, right? This is like a very excellent, very beautiful example showing how the theory can help us, right? So perceptron, the support vector machines are looking into minimizing the generalization error bound, right? And based upon their observation, right? They look at if I want to train linear classifiers, how to make the generalization error bound to be as small as possible, right? And they relate to the data-driven margin, right? Data-driven VC dimension. If you have some idea, right? You have some you can recall anything about that, right? We're not searching over the entire space of linear classifiers. Instead, we look at the subset of linear classifiers whose margin is at least some value, say gamma, right? And then there's a famous theory showing that, okay, the VC dimension, meaning the complexity of this small subset of linear classifiers, is directly related to the margin. The larger the margin, the smaller the VC dimension, right? That motivates the learning principles of vacuum machines. We want to find out the linear classifiers who has the largest margin, right? So kind of like minimizing the term in the generalization error bound determined by the VC dimension. So we're not asking you to recite what's the form of the generalization error bound and how it involves the VC dimension. But we just want want everyone to understand how this support vacuum machine, like maximizing the margin, how is this principle derived out of this chain, right? Computational learning theory, agnostic learning, generalization error bound, and data-driven VC dimension. Right? And then we kind of like formulate the learning objective for support vacuum machines. At the beginning, we just the straightforward formulation will incur a nested optimization problem, like max-min problem. That's very hard. So we kind of leverage the property of linear classifiers. What kind of property? The weights, when you arbitrarily skew them with any positive number, it won't change the classifiers. So you put additional constraints and then remove the inner optimization problem, right? Then we lead to the hard SVM, we lead to the soft SVM, and then we figure out how to solve this soft SVM problem using stochastic subgradient descent, right? So this, I mean, the topic and the content for support vacuum machines are a little bit intense, and they consist of like a series of logic chains, right? In both the learning principle and also the learning problem formulation, right? But every small step is relatively straightforward, but you just need to connect all those small steps together. And then we talk about how to consider a dual formulation of SVM. Right? This is purely from the optimization perspective. Right? We introduce what is Lagrange form. Right? How do we convert any constrained optimization problem into a minimax optimization problem for Lagrange function? Right? And we consider dual form. That just means like you switch max min. Right? And then by simplifying the dual problem, we found another formulation of SVM in the dual form. In that one, you just need to optimize the Lagrange multipliers, right? And why should we consider that? Because the dual form of support vacuum machines allow us to easily extend it to a nonlinear classifier, right? You don't need to like memorize every detail right now. I just give you a lead to piece them together, right? And we hope like you can find some time to quickly going through slides following this lead, right? Don't get lost. So basically the dual form of SVM, you'll find that, okay, what do you need? You just want to compute the dot product between every training input feature vector and test input feature vector, right? And naturally it involves the kernel trick. Remember, what is kernel trick? What is kernel trick? Anyone recall? Yes, exactly, right? That's the essence of kernel tricks, right? So want to extend a linear classifier to nonlinear, what's the most straightforward way? We just come out some like smart feature mapping, right? Typically in a high dimensional feature space, I do some feature mapping, and through the dual form, you see that actually what you need to do is that you first perform the feature mapping or lifting, right? And then in this high dimensional space, you compute their dot product. The only concern comes from the computational cost. And because this feature mapping is really very, very high dimensional, you don't want to explicitly compute them and then do the dot product, right? That's why we use this kernel tree. Kernel tree means that, okay, I can compute everything in the original feature space, but the result is equivalent to performing some like very high dimensional, sometimes even infinite dimensional feature mapping, then do the dot product, right? So through the dual form of SVM, it's very easy to inject or apply this kernel trick. And once you apply this kernel trick in the dual form, you literally convert SVM to a nonlinear classifier, right? That's the whole point of the SVM. And also, you should know how does this term, right? How are these terms like support vectors come from, right? It comes from the dual form solution, right? So remember the weight vector. The true weight vector is actually a linear combination of a set of training examples, right? You see that not all training example will contribute to the final weight vector, right? So I think this one needs to worth writing out, right? We actually from the dual form know that the optimal weight vector is up to a linear combination of a set of training examples, right? It is just their linear combination of the training examples. Of course, you're going to multiply with the label. The label is either 1 or -1, right? So actually, the true weight vector is only decided by a small set of training examples. This set of training example is called support vectors. Okay? And also, we know that support vectors are, oh, by the way, I want to ask, where do support vectors stay? Where are they? Yeah, it's not outside the margin, right? They have to be on the margin or inside the margin. So that's the funny, right? That's the funny things, right? So it looks like the most examples which are correctly classified by linear by our support vector machines, they have nothing to do with the weight vector, named the classification boundary. The classification boundary only determined by those bad examples, which break into the margin, right? But that's what you can see from support vector machines. Okay. So this all about SVM, right? And then the next important topic is about artificial neural networks, right? I guess the formulation of neural networks is pretty straightforward for everyone. You just it's like build up a carbine with a set of like wheels, right? It's just you have some basic blocks, basic bricks, right, or basic units. So you just put them together, stack them together. You got neural networks. You can make your neural networks as large as possible, as deep as possible, as wide as possible. It's just flexible, right? So the key thing we should be really cared about is how do we efficiently train neural networks? That is the backpropagation, right? And backpropagation, the essence of backpropagation is just a very smart leverage of the chain rule. And that's it, right? So we sequentially we select an order to compute those partial derivatives, right? That is from the output layer all the way back to the input layer. So that's why it's called backpropagation, right? And every time we just catch the partial derivatives for every neurons in the current layer, we can reuse this intermediate results to calculate the partial derivative with respect to every neuron and weights in the one in the one layer below, right? We just keep doing this until we reach the bottom layer. Then we finish the backpropagation. So again, we want to ask you to write down some particular process of backpropagation you have already done, or probably you are doing it right now, like in your homework 5, right? But we just want you to know what's the essence of backpropagation, right? Essentially, this is just a smart execution of chain rules. And the final thing is just about logistic regression and Bayesian learning. So we just want request you to understand what's the Bayesian learning, what's the notion of Bayesian learning, right? We have two notions. One is to learn a probabilistic concept. That is what logistic regression does, right? And another thing is to involve like probabilistic criteria in searching, right? Which we don't have time to introduce another example. It's called naive Bayes, but you just should have like concept that okay, maybe I can put a prior over the hypothesis space, and then I give a likelihood that is given any particular hypothesis, what is the chance you observe such data. You combine them together, you find out the most probable hypothesis given the observed data. So this searching procedure forms another notion of probabilistic learning. Okay, so basically we can characterize machine learning models into linear models and nonlinear models. We have introduced a lot of linear models, and based upon that, we introduced nonlinear models. One thing you should be very clear: decision trees, AdaBoost, random forest, they are nonlinear models. Although they look very simple, right? They're intuitive, but they're not linear models. They're nonlinear models. And we can also characterize machine learning models into probabilistic learning and non-probabilistic models, right? And there are several concepts about computational learning theory. So what is PAC learning, right? Probably approximate correctness, right? So you should have some like basic understanding about PAC learnability. So it's just to give you a way to categorize efficient learning algorithm and inefficient learning algorithms, right? Right. And what is the sample complexity bound? What is generalization error bound? We have just discussed, right? With dimension, right? Why? So here, we would like to know what is motivated? What's the motivation of this dimension? Why people propose? Why did people propose this concept? Any thought? Why did people invent this dimension? No one recalled? Yes, exactly, right? So don't forget don't forget the motivation, right? The most important thing is actually the motivation, it's not definition. So we have in the computational learning theory, right? When we did a bunch of analysis, right? We found that okay, to characterize the sample complexity bound or the generalization error bound, right? We do need some kind of metric which quantified how complex of your hypothesis space, right? That will be straightforward if your hypothesis space is finite. It's really just the size of hypothesis space. However, in many cases, you're dealing with infinite hypothesis space. Like even for linear models, your hypothesis space is infinite. Why? Why for linear classifiers or linear regression, your hypothesis space is infinite? Yes, exactly right. Even they have a like very simple structure. It's just a dot product between a weight vector and a feature vector, right? But those weights are continuous. You have infinite, uncountable many choices, right? So they have there. So that means like you can't directly look at their size of hypothesis space because their size is infinite, right? We have to come out another amenable measurement, right? In most cases, it should be finite to compare different complexities, right? That's how this basic dimension was motivated, right? And then you should understand the definition of this dimension, right? And how is the large margin principle derived by the generalization error bound? It's just to be clear about this logic chain. And also learning principles, right? We talk about empirical risk minimization, but this term just means that you want to minimize the training loss. You want to fit the training data to be as good as possible. Then we found that this is not good because you have some overfitting issue. So later we talk about the regularized risk minimization principle, right? Like SVM, map estimation for logistic regression. So you have an additional regularization term to penalize overcomplicated hypothesis space. Right? It turns out that one will be easier to give you a better generalization error. The risk minimization comes from the computational learning theory literature. They call it risk. Well, to me, it's nothing. It's just loss. They're interchangeable, but the term they use is called risk. It's just the name. Another question. Okay, so then from the Bayesian principle, we talk about map estimation and the maximum likelihood estimation, right? So they all have like well-defined probabilistic meanings, but we also need to be aware their connection to BRM and RERM. So basically, maximum likelihood estimation, you can view it as another way to describe the empirical risk minimization, and maximum a posterior map estimation, because you have to maximize the log prior plus log likelihood, right? So this log prior actually serves the regularization term. So maximum map estimation actually can be viewed as a way of doing regularized risk minimization. Okay, learning algorithm. We mainly talk about gradient descent and stochastic gradient descent. Right? I guess both algorithms are relatively straightforward, but we should be aware of their advantages and disadvantages. So what's the main advantages of stochastic gradient descent? Yes, exactly, right? That's why in large data scenario, people always favor stochastic gradient descent. Why? Because it can update model much more efficiently and frequently than gradient descent. Imagine you have like 1 billion training examples. If you do gradient descent, you have to go over the whole 1 billion training examples together to calculate the exact gradient and update model parameters, right? That's too slow. But if you use stochastic gradient descent, like you can even say one example, update model, one example, update model, right? So like going through the whole training data set for once, I can update the model for 1 billion times, right? Which is much, much more efficient than gradient descent. But on a small data set, for which you compute the gradient descent, the cost is not that high. The gradient descent is, of course, is better choice because your updated model is the exact gradient, right? There's no approximation error. It will convert faster. Okay. And some kind of like practical suggestions, mainly is about hyperparameter selection, right? So we talk about two strategies to do hyperparameter selection. One is that we're gonna separate the training data set, right? We can pick up part of them. We have some like holdout data set. We just look at how the training, along with the training, what's the performance on the holdout data set. Right? That's one way. Another way is that I don't want to use holdout data set to reduce the number of training examples, right? So I can perform cross validation. But cross validation is really much more expensive. Okay. The last thing, review suggestions. Again, go through all the lecture slides, trying to understand details, and go through the homework problems. And but you don't need to go through the programming problems. And wish everyone good luck. Right? Any questions so far? Okay, great. So the remaining about about half an hour to 40 minutes, we want to share some experience in the practice of machine learning. Hopefully, after all, I believe everyone, when you register this course, you're not just trying to say, okay, I'm taking some machine learning class, right? You want to, in some sense, like apply machine learning in whatever problems, like perhaps address your research problems, probably applying your in your work, right? So I want to give some practical advice for building machine learning applications, right? So basically, we want to talk about three things, right? First, how to diagnose your learning algorithm. How to know what's the problem, what's your current problem of your learning algorithm, right? It's not, in many cases, it's not like directly, it's not straightforward when you say the number, right? You have to, you have to check whether your learning algorithm is underfitting or overfitting, and then take actions. And then how to perform error analysis, right? Meaning that whether this metric you're choosing actually reflect the performance of your learning algorithm. We see some cases, if you simply use classification accuracy, it doesn't reflect the performance of your model at all. And finally, we'll talk about in practice, how you're gonna inject machine learning into your task, right? We'll talk about the industry, like people won't allow you to do very serious research and investigation and step-by-step approach. Instead, you should move fast. You should do quick iterations rather than those bottom-up research. Right? Okay, so the first topic, right? How to diagnose the problem you're learning algorithm, right? So suppose you train SVM or logistic regression, right, for spam email detection, right? And you follow the best practices for finding hyperparameters like cross-validation, right? And your classifier gives you only 75% accurate, right? And then you should diagnose where the problem is, right? And how do you further improve it? And here we're now assuming the implementation issue, right? We're assuming there's no bug in your code, right? After all, implementation is mainly from the basic programming and computer science skills, right? It's not about machine learning, right? Okay, so there are there are a variety of ways to improve your model, right? But you need to know how those commonly used approaches potentially address which aspect of model, right? So for example, we can consider adding more training data. Right? This is the most straightforward idea, right? Or we can consider incorporating different set of features. Perhaps we can use more features. Perhaps we can use fewer features. Perhaps we can use another set of features. Right? Or we can consider how to improve our training process. Basically, we need to run more iterations, right? So previously just run 100 iterations. Right now we run 1,000 iterations, right? Or we switch to a different optimization algorithm, or we switch to a different classifier, or we add some regularization term, right? So you see that there are so many choices, and just like blindly combining all those kind of like methods are tedious and also prone to errors. It depends on luck, right? So we need to make this improving process to be more systematic and more efficient, right? That means like we should first diagnose what's the actual problem of our model, right? And then if once we know, okay, this is because of this problem, then we can find out the corresponding, we can identify one of the action to address that, right? So here are a few commonly seen problems, right, in machine learning practice, right? So perhaps your current model is overfitting, right? Meaning that it has high variance, right? Or perhaps your model is oversimplified, so it's underfitting. Right? A third one could be your learning process issue, right? Your learning actually not converge. Right? That's about training process, right? And finally, maybe your metric is wrong. You're not choosing appropriate metric to quantify the success or failure of your algorithm, right? Okay, so let's see those problems one by one, right? So first, overfitting, right? How could we say whether your machine learning model is overfitting or not? Yes, exactly, right? So just to follow the definition, right? The overfitting typically means that, okay, you have a very high training accuracy, almost 100%, but the test accuracy is relatively low, right? So there's a big gap between the training accuracy and test accuracy, right? That means the model explains the training set very well, but poor in generalizations. Very likely is kind of fake to the noises on errors in the training data, which kind of mislead the model, right? But there are also cases that your model are oversimplified. They're underfit, right? So what's the typical behavior of underfit? Yeah, both training and test accuracies are too low, right? Unaccepted low, right? So that means the model cannot represent a concept or cannot approximate the concept well enough. So that's another interesting thing. Actually, in practice, perhaps you'll first see underfitting first. Like So if you see the training accuracy or training error doesn't go very low, you should try to increase the capacity of model first. In most cases, like as long as your training data is large enough, overfitting is not that big deal. But if your model is not expressive enough, you see that okay, it even cannot fit the training data well, then your model won't generalize well. Okay, then how do we simply classify these two problems, right? One often used trick is just look at the learning behavior. Right? We can look at along the increase of training data, how does the error vary, right? So here is the change of the training error, right? So, and the blue curve shows the change of the test error or the generalization error, right? If you see that the test error and the training error between them, there is always a large gap. Of course, when you increase the training data, the gap is kind of like reducing, right? But there's always some kind of big gap that indicates you have a overfitting issue. Okay. Then what can we see from underfitting? Underfitting, you will see like typically the gap is between the training and test errors are reducing quickly with increased data, but you see that the error are kind of like both converge to the high level. That's the underfitting issue. So by looking at those curves, you can quickly know, okay, whether your current model is overfitting or underfitting. And then we can take actions. Right? So let's see among those actions, which one will help address overfitting, underfitting. Right? So first, how about we increase training data? Or in other words, like increasing training data will help address which problem? Underfitting is not very. Underfitting means that the model itself is not expressive enough, right? You increase the data, your current data, it has already not able to fit very well, right? Increased data won't help. Yeah, that's another strategy. Right? Let's first talk about the increased training data, right? Increased training data will help what? Overfitting, right? Because overfitting means that your model is too complicated, right? The data is too small, right? It's trying to fit the data so well, including those noises, errors, right? But now if we keep increasing data, right, you know, the data will be more and more representative for the whole data distribution. It will kind of like effectively suppress overfitting issue, right? And use more features. It will help with underfitting. Why? Because you increase the model capacity, right? Because you increase more weights in your model. Imagine you're dealing with, you're using linear classifier or linear regression, right? So you add more features, mean that you increase the number of model parameters. You're trying to increase the capacity of model. So it could help with the underfitting. And use fewer features, it can help with overfitting. Why? Yeah, it's kind of reduce the model size, right? It can reduce the number of model parameters, right? And third strategy will be use other features, incorporate a set of other features. Well, then the consequences are relatively hard to see beforehand. It could help with both overfitting and underfitting, right? And that really depends on which particular set of features you're going to incorporate. Right. And for the training process, right, we would like to emphasize, sorry, if you add some regularization term, it could help with overfitting. Why? Yes, exactly right. You put some regularization term. This regularization essentially is to penalize overcomplicated hypothesis space, right? So that's another effective way to alleviate overfitting issue. Okay. So now we have talked about overfitting and unfitting phenomenon, and how do we what kind of like strategies we can use to alleviate these two problems, right? And third one I want to talk about is how do we examine your learning behavior, right? So basically, how do you conclude that your training process is okay? So this one can be done, like I believe everyone has done this before, right? In your homework, I want to look at how the training objective function varies along with the iterations, right? So you will see that from the figure, it's very hard to say whether your optimization process eventually converges or not, right? But you can see the trend. You could say this is objective function, right? We're assuming we're minimizing objective, right? So you should see the objective along with more and more iterations is the decrease of objective is less and less obviously. It seems converge at some places like here, right? But in many cases, you will see something like this, right? So it looks like you still have the trend to decreasing. You're not really reach the value, right? But it's okay. I mean, meaning that in practice, in most cases, you will see something like this, right? It's very hard to guarantee your objective is no longer decreasing anymore because you're doing numerical optimization, right? There's always some numerical issues here, right? So this is also a good trend, meaning that your training process is working normally. But if you say your learning curve are kind of like fluctuating very wildly, so this definitely means your learning failed. Your optimization is problematic, right? Because it doesn't show any trend. It just go up and down, right? And then you need to look at what's the problem. It's very likely that your learning rate is too large, or your optimization package is malfunctioning, and so on, right? But once you see that, you should know this is there is something wrong, right? And another thing we should be aware that if our objective function is convex, then no matter starting from which place, you're gonna eventually converge to the same global minimum. So you can try with different random seeds and see whether they eventually convert to almost the same place. Right. Okay. The last thing about the learning, especially when you use the stochastic gradient descent, right? You might not be able to see this so smooth curve, smooth trend of convergence. You will see it's kind of like a perturbation, something like this. So that's reasonable because you're using stochastic gradient descent, right? The stochastic gradient is not the true gradient; is a quite crude approximation. But you should still see from these small perturbations the convergence trend. If you see this trend, that means your learning is working, the functions normally. Okay, that means if you want to watch whether your training process is normal or abnormal, you should track the objective function and look at the convergence. So that's why in many like modern systems, like maybe how many have you have heard of TensorBoard? Okay, if you use TensorBoard, it's kind of like developed for for the monitoring of learning process. They provide you some kind of learning curve. You can look at how your learning process is progression, right? If you see some kind of big trend of a stochastic gradient descent, that basically means like your learning, the learning process itself is normal. Any questions so far? Okay. So the last thing we want to talk about is about metric. Right? So this is actually quite important, although it's not emphasized in our class. The reason is that in our class, or even your own research, you will find this metric are kind of like some common public acceptable metric, right? You can use mean square error, root mean square error, relative L2 error, and so on, right? They're well defined, right? But in practice, because the problem you're doing, many cases are kind of application specific, it's quite unique, right? You just apply those commonly used metric, that might not be, this might not be appropriate, right? So, for example, accuracy of prediction is one most common measurement. But if the data set you're dealing with is highly unbalanced, then accuracy may be misleading. For example, suppose your training set have 1,000 positive examples and only one negative example. And if you have a classifier that always predicts positive example, obvious that classifier is not correct, right? Is a very poor classifier, but your accuracy will be 99.9%, right? So obviously, this metric, the accuracy of prediction, is very misleading in this concept, right? In this context, right? And for unlabeled, unbalanced labels, right? How can we, which kind of metric should we use? So several other metrics have already proposed to address this issue. For example, we can use recall and precision, and then we do a harmonic average about precision recall. We call it F measure, and also the area on the curve is another good measurement, right? Which are used as a default metric in our Kaggle computation task, right? But this is just the one example showing you that don't just apply some existing metrics directly without thinking your particular application and your context. Right? Otherwise, it might lead to some like misleading results. Okay, error analysis, right? So this is talk about once you inject a piece of machine learning component into a big system, right? And then you look at the overall system, you want to debug what's the problem for each component. Right? So in our class, we're focusing on developing machine learning code, machine learning algorithms to addressing some particular problem, right? That's for class, but in practice, right? In practice, machine learning is just one part of the giant system. And this is just one example, like saying in an industrial system, like if you go to any internet company, like in Facebook or in Google, right? Their online advertising systems super complicated. Like machine learning is just one part, right? And for example, in this system, right, we need to first do some configuration, and then to do data collection, like web crawling, right, and feature extraction, and then data verification, and then do some ML code and do some analysis, and also you need to interact with machine resource management, and you have to do with like some process management tools. And then all those requests are deployed in a servicing structure, and the servicing infrastructure is also done by some monitoring system and so on. It's super complicated, right? And your actual work, I mean, if you go to the industry, if you work as a research scientist or research engineering in those places, right? And you already have some like overall metric. And then you're asked to improve something, right? And then the first step you need to know is that how do you correctly analyze the problem for each component, right? You need to identify a problem before you really start to improve, right? So generally, machine learning plays a small role in a larger application, like say pre-processing, feature extraction, data transformation, and so on, right? Then we would like to know how much do each of those contribute to the error, right? That's why we should perform some kind of error analysis. So here we'll give a concrete example. Using natural language processing as the example, right? So a typical text processing pipeline is like this, right? So this is a text, right? You have a big, you have a big set of text documents. Right? You're going to first tokenize those documents, right? Meaning that I'm going to extract those words, and perhaps I'm going to do some post-stepping. I remove, the tense, the plural, singular, and so on, right? To standardize the representation of those tokens. Then I do some kind of part of speech tagging, and to get some like basic semantic information, and then I do some part of speech tagging, and those information and the words and tokens itself will be do some like a semantic parsing, right? You have some parsing trees, and those parsing trees, their information all together will be sent to an ML-based application to perform some classification or sentimental analysis or recommendation and stuff. Right? So each of these could be some machine learning driven model or deterministic, but they have errors. Right? They're not perfect. Each component is hard to see perfect. Right? This component will have some error, right? But this error will propagate and accumulate throughout this pipeline and eventually give you some final error. Right? Then a question will be, how much do each of these contribute to the error of the final application? Right? How can we know that? Any thought? How can we debug this system so that we know, okay, which component in this pipeline is the bottleneck of the system? Right, you're right. Let me put it more explicit, right? So do this is kind of like tedious, but it's but it's straightforward actually. So we want to know which part contributes the biggest error or contributes has the most contribution to the bottleneck. How can we do that? We just can plug in the ground truth for each intermediate component and say how much the accuracy of the final system changes, right? And then we'd like to know, okay, what's the problem? Right? For example, if we just run the whole system, meaning that we do this end-to-end prediction, the accuracy is only 55%, right? It's relatively low. Of course, it has a large room to improve, right? And then we're going to replace each component by the ground truth. Of course, I need to perform some kind of large test, right? And then I given this set of documents, I know the ground truth words, meaning that those words, I did some like post-stemming, I did some like removing and standardization, and then I plug in the system, and I found that the final prediction accuracy increased to 60%, right? So there's some like improvement, but it's not super big, right? And next, we want to examine the effectiveness of parse speech tagging component. How can we do that? We replace this component by the ground truth as well. I did some like a manual parse speech tagging. And then we found that the end-to-end prediction accuracy rises up to 84% accuracy, right? It's a big improvement. Increased by 24%. Right? And next, we're going to replace the parsing tree results by the ground truth. And then the accuracy further increased to 89% accuracy. And finally, of course, if this ML-based approach is replaced by the ground truth, it will be 100% accuracy, right? So now throughout this list of results, which component can we conclude to have the biggest bottleneck? Which one? Obviously, this is part of speech tagging, right? Because once you replace part of speech tagging component by the true part of speech tags, the improvement is dramatic, right? Improvement is much larger than any other improvement. So that means the error in the part of speech components hurts the most. So we should first try to improve this component, right? We should try to overcome this bottleneck first, right? And once you have make your inject your new part of speech tagging, you can do this again, and then see which one is the biggest bottleneck and keep improving. And this procedure can be iterative. Right? So this is called ablation study, right? And this ablation study is also saying with features. Suppose we have a collection of features in our system as well, but we don't know which features are giving us the performance. Okay? We can evaluate a simpler system that progressively use fewer and fewer features to see which features give the highest boost. Okay? This is called feature engineering. Okay? But overall, the principle is that it's not enough to have a classifier that works. It is useful to know why it works. Right? So, because once we know why it works, we can come out additional ways to further improve the system. Right? For example, I know, okay, this type of features are useful. Then we want to like find out more data resources which contains those features and then import them into the current system for the further improvement. So never try to just maintain some black box system. That's not good, right? Although in research, like people kind of like think that this black box system, black box models are kind of magic, but in practice, especially in engineering practice, black box doesn't mean good things. Right? You're trying to make it to be as transparent as possible. Okay, so the last thing is that how do we develop machine learning for our favorite task? So suppose our task is like this, right? So you want to build a classifier that identifies whether a real physical fish is salmon or tuna. Right? How do we go about this? We probably can have two strategies to develop a machine learning method. The first one we call the slow approach or bottom-up approach. What's that? Right? We first carefully identify features, collect the best data, and design the software architecture. Maybe I can even design some new learning algorithm from scratch, right? And once every component, everything is ready, we implement the whole algorithm and the pipeline. I hope it works. So doing this is quite like systematic, quite rigorous, and perhaps it's a good approach. And maybe you can even produce a new learning algorithm in research. But in industry, if you're doing this, you're likely to be fired. Right? So this is the most ineffective way of doing this. So in practice, people will favor more to this so-called the hacker's approach. So I'm not gonna wait everything is ready or everything is perfect. Instead, I just use whatever data in my hand, whatever features in my hand, and then I quickly implement something. I probably just use most naive algorithm, most stupid approach, like say, I just linear classifier, a linear regression or whatever, right? And then I look at the performance and use all those diagnostic tricks and error analysis method as we discussed to find the problem and then iteratively make it better and better. So this is how, in practice, people are developing machine learning models because people want to say something first wrong and give you some results and see some quick iterations rather than wait for 1 year until your first version of our algorithm come out. Okay. So the advantage is that it can have a faster release. It will have a solution for your problem very quick. So in practice, when you use machine learning approaches to address your task, go with the hacker's approach. Okay, any questions so far? Okay. And also throughout your machine learning practice, please be aware whether you choose the right evaluation metric. Right? That's really, really important because when we go to the company, you know that your boss will not only look at your outcome, whether you have developed a new machine learning pipeline, will also say they'll also say whether your metric for evaluation can truly reflect the satisfactory of the users. This is actually very important because like many years ago, when I was an intern in Yahoo Labs, at that time Yahoo was still like a good, famous, a top tier internet company. Right now it's still there, but perhaps less people knows that, right? So there a lot of like meetings are talking about whether your evaluation metrics is correct. This is really important, right? A second thing, you should be aware of the contamination. Right? So this is some common mistakes, even for highly experienced research engineers. Like if you overlap the training data with the test data, then you have to redo everything, and you have to make sure your training and tests are completely separated. Right? So whenever you see your test performance is so good, don't celebrate. First, check whether your training, your tests, your training set is contaminated with a test set. And be aware of bias and versus variance trade-off, namely overfitting and underfitting. Be aware that intuitions may not work in high dimensions. This is also true, right? Because I mean, our intuition is just at most 3 dimensions, right? Because we're living in the 3-dimensional world. But in machine learning area, you often have to deal with data with thousands and even tens of thousands dimensions. So the intuition might not be correct. You have to accumulate a lot of experience and you have some rough idea about okay, which direction should have a higher probability to succeed, right? And also don't believe too much in theory guarantees, because many theory, if you rigorously look at their statement, you see a lot of like assumptions are made, and many papers they actually they prove theories just for easier application. It doesn't. They have to make very many unrealistic assumptions. That's why the theoretical guarantees in practice may not be may only be theoretical. You still have to do a lot of experiments on real data. And big data is not enough. Although big data is really useful, people have found that the value of the big data, right, with so much data and also a large computational power, like we can see the incredible success of current machine learning applications like generative models, right? Like video generation, like large language models, right? But it doesn't mean like big data is everything. Actually, you have to know how to which thing is the main driver to make your learning well. Right? For example, even for large language models, it often talk about wrong things, right? It's not doing correct in every aspect. Like for example, when I use that to check references or to summarize papers, it often gives you wrong statement, right? So you have to be aware of the limitation of the machine learning. It's not magic wand, right? It also has its own limitation. Okay, so in your practice, you should leverage the domain knowledge as much as possible, right? And which model is the right one for this task, right? This one, I mean, this kind of knowledge comes from your practice or comes from your colleagues, right? So don't try to do everything from scratch, right? And you should know which learning algorithms works better, right? So we know in neural network training, almost everyone is using stochastic gradient descent. More specifically, almost everyone is using a DAM algorithm, right? But in other scenario, it's not like this, right? And also, feature engineering is crucial. Your research and your class project won't ask you to do this because it's really too tedious. But in practice, this is really important. Actually, it's even more important than you design a machine learning model itself. Okay. Miscellaneous advice, right? In practice, don't try to build up a super complex model first, right? Try to start with a simpler model first, right? If it turns out to be work very badly, it doesn't matter. At least it form a baseline and that you can improve upon. And also by quickly deploying and testing those simpler models, you will find out what's the problem of those models and give you the right guidance to further improve upon that. Another rule of thumb is try to use ensemble. If you cannot improve your models anymore, try to use some ensemble, like bagging approach. And third one, maybe even fundamental, right? You should think about whether your problem is worth machine learning. Right? Maybe some problems are not suitable for machine learning. Right? So again, don't think machine learning is so versatile it can address everything. It's not like that. I should first figure out why machine learning could help. Okay, that's all about our advice, and thanks for your efforts throughout this semester. This course is going to be very tough, and I'm very happy to see everyone stick to the end. I wish all of you a great success in the future. Okay, and again, and hope everything doing well, like on your final exam. That's our last thing. Okay.